let's do a simple example. Here I have an example where I have this right triangle, and given is the length of one of the legs, 3, and the length of what's called the hypotenuse, 5, and we've drawn in an angle alpha. And what's asked of us is to find cosine alpha, sine alpha, and tangent of alpha. Now finding cosine alpha with the given information is relatively straightforward. Cosine of alpha, that is the adjacent side length over the hypotenuse, so cosine alpha is 3/5. However, sine of alpha is not so straightforward since we need the length of the opposite leg, and we'll divide that by the hypotenuse. But we can find the length of the opposite leg by using the Pythagorean theorem. Now remember, if you have some triangle, which is a right triangle, it's extremely important if you're going to use the Pythagorean theorem for your triangle to be a right triangle. The Pythagorean theorem is not true if you have a triangle which does not have a right angle. But if you have some triangle, some right triangle, and the lengths of the legs are a and b, and the length of the hypotenuse is c, then the Pythagorean theorem says that a squared plus b squared is equal to c squared. And again, this is only true for right triangles. Only true for right triangles. And notice that the length of the hypotenuse is on the right hand side as well. That is also important. So if we call the length of this unknown side a, then we can figure out a by writing the Pythagorean theorem that a squared plus 3 squared is equal to 5 squared. And we can go ahead and solve for a. So a squared is 25 minus 9, which is 16. And that means that a is going to be plus or minus the square root of 16, which is 4. Now a is a length, so it's going to be positive. And so we know now that this a is 4. And that will allow us to figure out what sine alpha is and tangent of alpha. Sine alpha is going to be opposite, which is 4, divided by the hypotenuse length, which is 5. And tan alpha is going to be the opposite length, which is 4, divided by the adjacent length, which is 3. And you can figure out the values of other trigonometric functions as well. For example, if you wanted secant alpha, well, that is the hypotenuse over the adjacent length, so that'd be 5 divided by 3. Now that we've done an example, I want to talk a little bit about notation. So I have drawn here two triangles, and they have their side lengths labeled A, B, and C. And this is going to be very typical in many different examples that you come across, that we use lowercase a, b, and c to represent the lengths of the sides. When we do this, there are two types of notations that are typically used for angles. The type of notation that I will frequently use is the lowercase Greek letters for my angles, and because this is a right angle in the lower right hand corner, we don't give it a name, but if I were to give it a name, I would give it the lowercase gamma. And we'll see later on that we will actually have to give this a name. But again, in the context of right triangles, we know that that's a right angle, so it doesn't need a name. We already know what the measure of it is. It's 90 degrees. In some texts, what you'll see is that they give the notation of capital Roman letters for angles. So capital A, capital B, and then this is a right angle, but if I were to label it, it would be capital C. I prefer to not use this notation, one, because in applications such as in physics and engineering and pretty much every other application, lowercase Greek letters are typically used instead of capital letters. And also, it can be challenging in terms of handwriting to distinguish a lowercase and a capital C. So I will always use the lowercase Greek letters in my drawings. Now, there's a couple other things to note that are important in the notation. The first is that if you have a right triangle, then A and B are typically used for the legs, whereas C is typically used for the hypotenuse. And secondly, the side labeled A is always opposite to alpha. The side labeled B is opposite to the angle beta, and the side C is opposite to gamma if it's not a right triangle. If it's a right triangle, it's just going to be this right angle symbol. And with the uppercase Roman letters, you see that the capital A is opposite to lowercase a, capital B is opposite to lowercase b, and capital C is opposite to lowercase c. So in essence, what I'm trying to say is I wouldn't draw a triangle like this with alpha there and b here. So it's just a couple pieces of important notation to recognize. Let's do an example practicing this notation here. So let's find the length of each side and the measure of all angles if beta is 30 degrees and C is 15 root 2. And let's go ahead and add on that this is a right triangle. So assume this is a right triangle and that we're following our notation that we just discussed. So what we're given is we're given the measure of an angle. We're actually given the measure of two angles. We're given the measure of this beta angle, and we're also given that there's a right angle as well. So we know the measure of two angles, and we know the length of one side. So let's go ahead and draw a picture of what this might look like. And your picture does not have to be to scale at all. In fact, I won't even make an attempt to make it to scale. That is, I won't attempt to make C equal to 15 root 2. I won't attempt to make beta look like 30 degrees. But of course I will label them correctly. So C, by our notation, is the length of the hypotenuse. So this is going to be 15 root 2. It's important that this length is 15 root 2 and not something like this over here. That would give a leg the length of 15 root 2. And then I have a right angle that's opposite to the hypotenuse, and let's label this 30 degrees. Now, you could actually label the angle that I labeled 30 degrees, or you could label this upper right-hand corner 30 degrees. I'm going to label the lower right-hand or the lower left-hand corner 30 degrees, and if you do that, then that will make the length of this side here b, because b needs to be opposite to the angle beta. This also forces this angle up here to be called alpha, and it forces the side down here to be called A. And I want to make sure I'm clear about this, so I'm going to draw another appropriate triangle that would be okay for this problem. So you could have drawn something with the following labels. So go ahead and erase these signs. We could have put 30 degrees in the upper right hand corner. If you do, then B is this lower side, because again B has to be opposite to beta. Then that would force this lower left hand angle to be alpha and A to be the side across from alpha. So either of these drawings are fine. What would not be okay is to label alpha to be the side, or excuse me, the angle opposite to B. So now that I have talked about that at length, I'm going to erase this drawing here and use my first drawing. And what we have to do is we have to figure out the length of each side and the measure of all the angles. Now, two of the angles have already been solved for. We have our 90-degree angle and our 30-degree angle, and we need alpha. Now, in any triangle at all, it doesn't even have to be a right triangle, the sum of angles is either 180 degrees or pi radians, depending on if you're working with radians or degrees. So this means that alpha plus 30 degrees plus 90 degrees has to be 180 degrees. And so if you subtract 90 and 30 degrees, you get that alpha is 60 degrees. So that is part of the answer here. Now we need to go ahead and figure out what A and B are to complete this problem. And there's a number of different ways you can go about this, but all of them involve using the definition of the trigonometric functions. One way you could go about this is you could say that cosine alpha, and we know what alpha is, so cosine of 60 degrees, that's equal to, you need the length of the side adjacent to alpha, which in this case is b. So that's b divided by the hypotenuse, which is 15 root 2. And now we know what cosine of 60 degrees is. It's 1/2. We know that from our previous discussions about the trigonometric functions, and so we can replace that with 1/2. So 1/2 is b divided by 15 root 2. And now that allows me to determine what b is. So b is going to be 15 root 2 divided by 2. And like I previously alluded to, this isn't the only way to figure out what b is. You could also use the fact that sine of 30 degrees would be opposite, which is b divided by 15 root 2. And you'll get the same answer. So if you say sine 30 degrees is b over 15 root 2, if you remember, sine of 30 degrees is also 1/2, and you get the same equation, which leads to the same value of b. So now we've figured out what b is in a couple different ways. Let's figure out what a is. Now, what I'll do here is I'll notice that if you have 30 degrees, then cosine of 30 degrees, that's going to be the adjacent length divided by the hypotenuse. And so cosine 30 degrees, that is a over 15 root 2. And cosine of 30 degrees, well, that is root 3 over 2. And so I can solve for a. So a will be 15 root 3 times root 2, which is root 6, all divided by 2. But like before, that's not the only way to figure out what a is. If we look back, remember now we actually know what b is. So we could say tangent of 30 degrees is b over a. And let's see if we can get the same answer. So tangent 30 degrees, that's b, and what did we find out b is? B is 15 root 2 over 2. So b over a, which is 15 root 2, all divided by 2, and divided by a, which we don't yet know. Well, I suppose we do, but we're trying to do this a different way, so pretend we don't know what it is. So then I know what tangent of 30 degrees is. Tangent of 30 degrees is sine 30 degrees over cosine 30 degrees, which if you remember back to our previous discussions is 1 over root 3. And so I can multiply both sides by a to get rid of a, and I can multiply both sides by root 3 to get rid of that root 3, and what I get is 15 root 2 times root 3 all over 2 equals a. And root 2 times root 3, that's root 6. So 15 root 6 over 2 equals a, which of course is the same answer. And finally, one more way to figure out what a is. I won't go through the calculation, but I'll show you what the calculation is. Remember, we know what b is and we know what c is, and this is a right triangle. Therefore, the Pythagorean theorem applies, and a squared plus b squared has to be c squared. And so we can write out, remembering that b is 15 root 2 over 2, that a squared, which is supposed to be unknown, plus b squared, which is 15 root 2 over 2 squared, is the same as c squared, which is 15 root 2, and you have to square c. So you can also figure out a from this equation here. And so at this point, I have figured out what a is. I figured out what b is. C was given to us, and we figured out what alpha is, and so that concludes the problem.